Okay, so now we're doing the next one, which is terminology, but it's terminology to do with everything we're just doing, like atomization and all that stuff. So explain the meaning of each of the following diesel engine terms: overlap, scavenging, afterburning, compression, and expansion. A very common question, came up in October 2022, June 21, January 2018. Explain the meaning of each of the following terms: overlap, scavenging, afterburning, compression, and expansion. Let's look at overlap first of all. Here's an explanation of each of these. Overlap. Overlap refers to the period in a four-stroke diesel engine cycle where both the intake and exhaust valves are slightly open at the same time. This timing is crucial for efficient operation. The exhaust valve starts closing near the end of the exhaust stroke. That's the exhaust valve closing. The exhaust valve starts closing near the end of the exhaust stroke. Intake valve opening a little before the piston reaches the bottom of its stroke. That's the end of exhaust. The intake valve opens. This allows some fresh air to enter the cylinder to help expel remaining exhaust gases. The benefits of this is the overlap period helps scavenge exhaust gases more efficiently and promotes a cooler intake charge due to the incoming fresh air. Number 2 was scavenging. The scavenging process of removing exhaust gases from the engine cylinder and replacing them with fresh air during the engine cycle. Wow. Scavenging is a process of removing exhaust gases from the engine cylinder and replacing them with fresh air during the engine cycle. This is essential for several reasons. The combustion efficiency. Proper scavenging ensures a mostly fresh air charge is present in the cylinder for efficient fuel combustion during the power stroke. So it's just sucking in. But how can it be like that? We would have thought it'd be, is it not mixed? Combustion. Proper scavenging ensures a mostly fresh air charge is present in the cylinder for efficient fuel combustion during the power stroke. Reduced emissions. By removing exhaust gases, scavenging helps minimize pollutants like unburned hydrocarbons, that's the actual fuel, and oxides of nitrogen, so that's NOx, in the exhaust. Cooler operation, fresh air entering the cylinder helps lower the overall engine temperature. Okay, so overlap between the exhaust gas and intake valves plays a critical role in the scavenging process. Okay, kind of really connected to each other. And then number 3 was afterburning. Afterburning, also known as exhaust gas treatment, is not typically part of a four-stroke diesel engine cycle itself. It refers to additional technologies used to reduce harmful emissions in the exhaust after it leaves the engine cylinder. So you just burn it at a high temperature to burn off any unburnt hydrocarbons. Common, and then, they don't get released into nature. With like the oil everywhere, you just get CO2, which is clean. Common afterburning techniques include catalytic converters. These devices promote chemical reactions that convert pollutants like NOx into less harmful substances. And diesel particulate filters, they trap soot particles in the exhaust, reducing their release into the atmosphere. Okay. Afterburning. Why is it called afterburning? If you're filtering using catalytic converters, you would have thought you'd be burning some of it. I'm sure there probably are. Compression is part D. Compression is a crucial stage in the four-stroke diesel engine cycle. So compression has an intake stroke and a compression stroke. The intake stroke is the piston moves down, drawing a mixture of air and fuel, air only in direct injection engines, through the open intake valve. Compression stroke. With the intake valve closed, the piston moves up, significantly reducing the volume of the air-fuel mixture within the cylinder. The compression dramatically increases the temperature and pressure of the mixture. The high temperature and pressure created during the compression process or during compression are essential for efficient fuel ignition in a diesel engine without the need for spark plugs. Yeah, so this is what I got confused about, is we're talking about diesel engines, right? So I thought, wouldn't you be mixing the air with the fuel before you inject it into the engine? And yeah, you do in a carburetor, but I think that's only for petrol engines, right? And then diesel engines, you inject it directly into the cylinder, so it has to have air from the outside in order to, it mixes directly in the cylinder is what I'm trying to say. You inject it in there, and then we're going to get to turbochargers later on, where we're going to be squashing that air in there as quickly as possible to burn more fuel in the same amount of space. Okay, so it makes a bit more sense now. Thanks for sticking with me. The high temperature and pressure created during compression are essential for a fuel ignition. All right. Expansion. Expansion is the power stroke of the four-stroke diesel engine cycle. Combustion under the high pressure and temperature from compression, the injected fuel ignites spontaneously. This burning fuel rapidly expands, pushing down the piston down with a great force. Expansion stroke. The expanding hot gases from the combustion force the piston down, rotating the crankshaft and generating power output from the engine. Combustion expansion stroke. All right, yep. The force exerted by the expanding gases during the stroke is ultimately what propels the engine. All right, drives the engine. October 2022. Explain what is meant by each of the following terms. Cetane number. I think that's right. Cetane number, calorific value, density, and viscosity. Right. So cetane number, it sounds like octane number. Octane, I reckon, is the higher value, and cetane is the lower value. Well, I did actually look it up earlier. We've got octane and cetane for slower burning and faster burning. So this is to do with it. It's like spontaneously combusting, and I got all that from a YouTube video by Vertasium, I think, on it, or Smart Every Day or something like that. Good stuff. Oh no, it was like the lead. It was a talk about lead and how lead controls this, basically. That's why we had lead in our fuel, and hopefully we don't have it so much anymore at all, hopefully. Explain what is meant by the following terms. So cetane number, that's going to be how easy or how hard it is to ignite it by autocombustion, after you compress it for the knocking and all that. And then calorific value is the actual energy present in the fuel. Density, well, that kind of speaks for itself, how dense the fuel is, how heavy it is. Viscosity, similar stuff, how viscous the fuel will be. These are just regular chemical terms. But cetane number and this octane number, and they're just in reference to how easy it is to ignite octane and cetane, I suppose. Here's a breakdown of each of the terms related to diesel fuel. The cetane number is a critical indicator of the diesel fuel's ignition quality. It represents the delay between full injection and the start of the combustion in the diesel engine. Higher cetane number indicates a shorter ignition delay. This is ideal for smooth engine operation, minimizing knocking and incomplete combustion. A low cetane number represents a longer ignition delay. This can lead to a rough engine operation, increased noise or knocking and incomplete combustion, resulting in higher emissions. Still for diesel, huh? That's weird. I guess you still got to regulate the fuel, because all this stuff I'm talking about is petrol with all the lead and stuff added onto it. Explain what is meant by the following terms. Oh, related to diesel. It doesn't say specifically diesel in the actual question. But the answer that we got here is talking about diesel, which is weird. But okay, maybe it is cetane is only for diesel. Yeah, maybe it's only used in diesel, and octane is used in petrol. Okay. Cetane number is similar to the octane rating used for gasoline. Yeah, okay, but the measurement, but they measure different properties. Okay, so it's just the opposite of the octane, but you use it in the opposite stuff as well. You use it in gasoline. Petrol is octane, and diesel is cetane. That's interesting. Calorific value. The calorific value, also known as the heating value, refers to the amount of heat energy released when a unit of mass of fuel is completely burned. It's typically expressed in units like megajoules per kilogram, megajoules, MJ, kg, that's too many letters, or British thermal units, BTU, per pound, blimey. Okay, a higher calorific value indicates the fuel contains more potential energy per unit mass. This translates to more power output from the engine for a given amount of fuel burned. Yeah, we do this in Jest 2 for fuel content, a bit of chemistry as well. And you end up calculating the power of the engine in watts because of that, but it's just the amount of actual energy in the fuel. So if you were to like eat it and you could digest it, then you'd get the same amount of energy out of it measured in joules. But you can do the same thing with a donut. You can work out the calorific value of a donut by burning it as well. So density refers to the mass of fuel per unit volume. Yeah, well, density is kilograms per meter cubed. It's typically expressed in kilograms per liter or pounds per gallon. Okay, well, when we do calculations in Jest 2, it's given as kilograms per meter cubed, as the same as water, usually. But all these are valid units, I suppose. The reason why it's kilograms per liter is because water will be 1, so it's relative to water in that case. So lighter than water, or relative to water, always probably going to be lighter than water. And density is important for several reasons. Fuel economy: denser fuels store more energy per unit volume, potentially leading to a better fuel economy. So I think that's the difference between petrol and diesel, right? I think petrol is much lighter for the same volume, and seeing as you buy it by volume, I think you end up spending more buying the petrol because you need more of it. Ethanol is very similar to that as well. It uses a lot of space. It's quite light. It's not heavy. So all the molecules are spaced out. They don't really pack together very well. So it takes up a lot of space, which means you need to have a massive fuel tank. It doesn't weigh that too much, but it's freaking massive. Okay, and it means you can't use it so much. You don't go so far. Fuel economy: denser fuels store more energy per unit volume. Okay, great. Potentially leading to a better fuel economy, assuming similar calorific values. Yeah, okay. Injector systems. Fuel injection systems are calibrated for a specific fuel density. That's much more important. Significant deviations can affect engine performance. All right, so your fuel injection system is really heavily reliant on or calibrated for the density of the fuel. Okay, viscosity. Viscosity refers to the fluid's resistance to flow. Like honey is really viscous. It doesn't want to flow very quickly. Runny honey, not the solid stuff. That doesn't flow at all, right? In the context of the diesel fuel, it describes how easily the fuel flows at given temperatures. It's typically measured in units like centostokes. Centostokes is typically measured in units like centostokes, which is CSTs. Oh my goodness, never seen that before. Here's how viscosity affects diesel engines. Cold starts. At lower temperatures, high viscosity can make it harder for the fuel to flow, hindering the engine starting. Yeah, so difficult to start in cold climates. Injection and atomization. Proper fuel atomization, breaking the fuel into fine droplets, is crucial for efficient combustion. High viscosity can make that harder to do. Yeah, try spraying honey through like a mister. It's going to be pretty hard. The lighter the fuel, the better. Pump wear. Fuel pumps rely on the fuel's lubricating properties. Very low viscosity can increase wear on the pump components. All right. So if it's harder, it's going to wear out the pumps a bit quicker. April 2023, with reference to the tube type heat exchangers, explain the purpose of each of the following: baffle plates, sliding tube plates, telltale ring, vent cock, and anodes. I just looked at this on a YouTube video, which is, what's his name? SVRE or something like that. It's really good. With reference to tube type heat exchangers, explain the purpose of each of the following: baffle plates, sliding tube plates, telltale ring, vent cock, anodes. In a tube type heat exchanger, each component plays a specific role for optimizing heat transfer and ensuring safe operation. Here's a breakdown of each purpose of each term. Baffle plates. Baffle plates are thin metal plates placed within the shell side of the heat exchanger. They serve several purposes. They direct the fluid flow. Baffles prevent the shell side fluid from simply flowing straight through the heat exchanger. They force the liquid to take the longer path across the tubes, maximizing contact time for heat transfer. Yeah, they go all over the place. They baffle the liquid, right? They confuse it. So it has to go all around the houses. It can't just go straight across. That's why they're called baffle plates, right? Can create crossflow. By strategically positioning the baffles, they can create a crossflow of patterns across the tubes. This ensures even more distribution of the shell side liquid and improves overall heat transfer efficiency. Shell side. Are you talking about shell side? Are we talking about hull? No. I have to look it up. Support tube bundle. Baffles can also help support the tube bundle within the shell, preventing excessive movements and potential tube damage. Okay, so they add a bit of structural integrity to it as well because they're plates. Sliding tube plate. The sliding tube plate is one of the two tube sheets or plates holding the tubes in place. Unlike the fixed tube plates, the sliding plate can move slightly along a defined channel. This movement allows for the thermal expansion, right, a thermal expansion accommodation. As the tubes heat up, they expand. The sliding tube plate allows for this expansion without putting undue stress on the shell or the tubes themselves. Okay, so they're allowed to expand a little bit. Leak prevention. The slight movement also allows to maintain a tight seal between the tubes and the tube sheet, minimizing the risk of leaks. Okay, great. So they can wiggle around a little bit. Sliding tube plate. Telltale ring. Telltale ring. The telltale ring is a small groove or channel machined around the edge of the fixed tube sheet where it meets the shell. It serves as an early warning system for potential leaks. Leak detection. If a leak develops between the tube and the fixed tube sheet, the leaking fluid will travel through the telltale ring groove, where it collects it together into one place. So if it drips, you can see it. The fixed tube sheet, the leaking fluid will travel through the telltale ring groove. Yeah, it will. Huh? The leakage plate. This groove provides a controlled path for leaking fluids to exit the heater exchange without mixing the two fluids being exchanged. That's a good idea. This allows for easier leak detection and help prevent potential contamination. Yeah, so when you're doing a heat exchanger, you don't want your two liquids to be mixing, especially if we're talking about something like oil on the inside of the ship and water from salt water from the outside of the ship, because you'll be pumping out a whole bunch of oil into the environment without even realizing it if you had a small crack in there. All right, so that's what the telltale ring is about. It's about leak detection. And it gives it a good exit as well. Vent cock. The vent cock is a small valve located at the top of the shell of the heat exchanger. It serves two main purposes. Air venting. During initial filling and operation, air pockets can become trapped inside the shell side of the heat exchanger. The vent cock allows for manual venting of these air pockets. Air pockets can hinder heat transfer efficiently. Pressure relief. In some cases, the heat exchanger might be subject to pressure fluctuations. The vent cock can act as a safety release valve, releasing excess pressure and preventing potential damage to the shell. I just realized what we're talking about. We're talking about a heat exchanger, and it's the shape of a big round tube. So it has a shell on the outside, and it's full of pipes and stuff on the inside, or in this case, baffle plates on the inside. So yeah, that explains that. And it can be used for any purpose. Heat exchanging. All right. So we got the pressure. The vent cock is basically a safety mechanism, so it can be vented during filling, and it can also, if it gets too hot because you're running the system too hot, or it just gets that way because you're running the system for a long time, it will release the pressure. All right, anodes. Anodes are sacrificial metal components placed strategically within the shell of the heat exchanger. They play crucial roles in the corrosion protection. All right, so if we're doing stuff like pumping cold seawater through here, then yes, we would have to have these inside of any complicated metal components to avoid corrosion. Yeah, galvanic corrosion. In the tube type heat exchanger, different metals, the tubes and the shell, can create galvanic cell. So there's different types of metal in the actual construction of the condenser, and it's easier just to prevent that rather than make the whole thing in the same type of metal. Leading to corrosion of less noble metal. Sacrificial protection. Anodes are made from a more reactive metal than the tubes of the shell. They corrode, preferentially protecting the other components from electrochemical corrosion. So yeah, sacrificial anodes, the same on the outside as well as on the inside of the ships. Anodes are typically made from materials like magnesium and zinc, require periodic replacement as they corrode. All right, usual stuff. January 2019, with reference to diesel engines, explain each of the following terms: top dead center, bottom dead center, piston stroke, swept volume, clearance volume, and compression ratio. We've done these before. We've done some of them. Top dead center, pretty easy, 1 mark. Bottom dead center, 1 mark. Piston stroke, swept volume, clearance volume, and compression ratio, or 2 marks. These terms all relate to the movement of the piston within the cylinder of the diesel engine and the resulting volumes created. Top dead center, so that's going to be the smallest volume, isn't it? That's the compression cycle. This refers to the utmost point of the cylinder that the piston reaches during its movement. At top dead center, the piston is as close as it can get to the cylinder head, so therefore it has the highest pressure as well. Bottom dead center is the complete opposite, of course. It represents the lowest point on the cylinder that the piston reaches during its movement. At bottom dead center is the furthest away from the cylinder head that it can get. Piston stroke. The piston stroke is the total distance that the piston travels between the top dead center and the bottom dead center, and essentially the length of the piston's movement within the cylinder. Yeah, so I was going to say the length of the piston arm, but it's not quite. It's the length of the piston stroke. Swept volume. The swept volume is the theoretical volume displaced by the piston during one complete stroke. So it's how far as the piston's moving, basically, up, down, within the cylinder. It's calculated by multiplying the cylinder's bore pi times the radius times pi r squared, basically, to get the cross-sectional area of the cylinder by the piston stroke, by how high it is. You're just doing the volume of a cylinder. We definitely do that in JES 1 for basic shapes, and we also do it just in JES 1. Okay, clearance volume. The clearance volume is the volume remaining in the cylinder at top dead center. So that's the bit that you don't squash, is the top of the bit of the air, a bit of volume at the top of the cylinder that doesn't get compressed, but it's full of compressed air and fuel. With the piston at its highest position, there is still some space between the piston head and the cylinder head. This clearance volume is crucial for several reasons. Combustion space. It provides necessary space for air or the air-fuel mixture to be compressed before ignition. piston expansion. The clearance volume allows room for the piston to expand slightly without contacting the cylinder head. The clearance volume allows for the piston to expand slightly, so because it gets to a higher temperature and it goes to a lower temperature during the cycle, so it expands just like a tiny little bit. That doesn't need to be that big, does it? Engine starting. Adequate clearance volume is necessary for the engine to crank freely without the piston hitting the cylinder head. Adequate clearance volume is necessary for the engine to crank freely without the piston hitting the cylinder head. Okay. F is compression ratio. Compression ratio was a comparison between the swept and the clearance. Compression ratio is a critical parameter in diesel engines and is calculated by dividing the total volume cylinder, that is the total cylinder volume, swept volume plus clearance volume, by the clearance volume. Here's the formula. Compression ratio is total cylinder volume with, I think it's the wrong way around. Let me just double check that. By dividing the total cylinder volume, oh no, it is like that. You take the total cylinder volume and divide it by the clearance volume. So the clearance volume is going to be small, and the total cylinder will be big. So it's like 2 to 1. So you just get a compression ratio of 2, which is a 2 to 1 ratio. It literally is a ratio. That's how you do ratios. Is you got the total cylinder to the volume of the other one, and you can just read it like that. If it's like 100 centimeters cubed down to 20 centimeters cubed, right? It'll be like that, or 1,000 to 200, it'll be you can just leave it like that as a 1,000 to 200 ratio, or you can simplify it down to, like, I don't know, like a 5 to 1 ratio or something like that. It tells you how much is being squashed. The higher compression ratio signifies a greater compression of the air or fuel air mixture in the cylinder, leading to higher efficiency. So same as always, higher efficiency, more power, better fuel ignition, okay, stuff like that. So higher efficiency, increased compression creates higher temperatures and pressure during combustion, improving fuel efficiency. More power, the higher pressure generated during combustion translate to more power output from the engine. However, there are limits to compression ratio. Due to factors like fuel ignition. Very high compression ratios can cause the air to ignite spontaneously before the intended ejection of the fuel, leading to the engine knocking. Can cause the air to ignite spontaneously, not the fuel. Before you even inject the fuel, if you compress the thing too much, the air just, I guess there's residue of the fuel oil still even in there before you inject more in there, so that can burn up. But like, what, the oxygen just burns? It just spontaneously combusts if you crush air enough? Might do. Engine design. The engine needs to be designed to withstand the increased forces associated with higher compression. Yeah, so this is what I was saying. You crank up the pressure inside your engine. Of course, you increase the output, but you also run the risk of blowing the thing apart. And generally, like, the bigger the engine, or the more well-designed the engine, the bigger the engine, like you guys are using, the higher the pressures you can get in there.